Hello. Thank you for joining the Texas Instruments New Product Update webinar. Just a reminder that this is a weekly series every Thursday at 10 a.m. Central. A few quick announcements before we get started. This webinar will be recorded and available online at ti.com/MPU. All phone lines will be muted, so if you have questions, please use the chat box and we will try to answer in real time, or you can contact your TI salesperson or field application engineer. Today's topic is TMAG 5115, low jitter and fast Hall effect latch. I will now pass it over to Manny Saltero for introductions.
Kelly. Okay, well, good morning, everyone. As Kelly said, my name is Manny Soltero. I am the position sensing product marketing engineer within Texas Instruments, and today we're very excited to talk to you about this TMAG 5115. We think it's a stellar device, and hopefully you're going to see the same after you look at some of the specs. But anyway, we're all excited about this device, so let's go ahead and continue with the presentation. Okay, so here's the agenda. What we're going to do is we're going to talk about a little bit about the Hall effect portfolio, because we've got quite a slew of devices that we've released over the past couple of years. So you'll see that our portfolio is actually growing very nicely. And then what I'll do is I'll cover the product overview for this new device. And then we'll sort of go over some of the key specs for this device, and system level benefits that you can leverage from this specific solution. One thing I would like to note is if you have any questions, go ahead and chat with Isaac Lara. He's already online as well. He's one of our apps engineers that is responsible for position sensing products. So if you got a question, feel free to chat with him, and then he'll try to provide responses via chat. And then if we have some time, we'll probably go ahead and maybe ask some questions that he might have received, and we can answer them as well. Okay? Okay, so we're going to try and fit this in within 30 minutes. I think we definitely can. I'm guessing that we'll probably have a little bit of time towards the end, but let's see how this goes. All right? All right, so let's go with the portfolio. So this particular portfolio shows where we are with our switches and latches. So switches and latches, as you know, are digital products, okay? These are digital output solutions that can give you a relative position of where a magnetic field is once it crosses that threshold, okay? So let me try and help you out so you can determine what the kind of products are in this eye chart of a slide here. So anything above this horizontal line is our high voltage portfolio. Anything below it is what we consider our low voltage, up to 5.5 volts. And then besides that, we also have this vertical line that splits the portfolio in half, and so that really details our switch portfolio. We have unipolar switches and omnipolar switches divided into this section here. By unipolar, as you know, it means basically that the device is sensitive to only a single pole. With omnipolar, this means that the device will be sensitive to either north or south pole, okay? Now, if I were a designer, I would always go with omnipolar. That way you don't worry about how your magnet is oriented toward the switch. But anyway, I just think overall omnipolar switch is more popular and I think better suited for many applications, strictly because of production costs. But anyway, this sort of gives you an idea of the portfolio from a switch standpoint. Just want to highlight a few things to also look at from this slide is, we've got all these hashed lines and also, a red outline as well. Well, that gives you an indication on the capacity improvements that we've done with our portfolio. All right, so what we've done is that if we're trying to increase the the capacity over the past couple of years, right? This has been an issue for many suppliers, not only TI. This is an industry-wide thing. So what we're doing is we're definitely increasing our capacity and improving upon that. What that means for you, the customer, is that if it's in a 300 millimeter fab, that means it's in the largest wafer we could possibly put our analog designs in. You know, it comes out of our Richardson fab, which is really the state-of-the-art newest fab that we have. And then also, if it is red, it's red outline, not only is it 300 millimeter, but it is also in the newest and latest and greatest process, okay, which what we call LBC9. So, so I think that if you have those together, I think it ends up being a very, very stellar solution. So we've got a ton of products, you know, the latest being, let me just highlight a couple of these. The TMAC 5123 is our latest in-plane sensor. It basically will be able to detect magnetic fields from the side of the package. So, you know, we label this as X or Y. So if you have your TMAC 5123, it will detect magnetic fields from the X direction or the Y direction, right? So it, look at the data sheet. I think what we have mainly is the X direction for the 5123. Most other solutions that we have are, and that's a traditional sense, is to have a magnetic sensitivity to the Z-axis, okay? And that's what a lot of these, that's where these Z stands for. A new other device that we have is the DRV5032 and TMAC 5231, which are really high, I would say, capability to deliver a high amount of units, high capacity, I should say, is the DRV5032 and the TMAC 5231. These are, you know, we sell these by the boatloads. So very, very popular solution. And these are general purpose switches, but perform very, very well. And then we also came up with the TMAC 5328, which is a resistor adjustable threshold. Okay, so that basically says that, you know, a lot of times when you have a magnetic sensitivity device that you might be, you know, thinking about, is it going to be 2 millitesla? Am I going to need a 4 millitesla? Well, in this case, you won't have to worry about that because you can purchase this device and you can adjust it, right? You can vary the magnetic sensitivity anywhere between 2 millitesla and I believe it's 15 millitesla. But anyway, with a single resistor, you can adjust your sensitivity level, which is kind of cool. Okay, now let's move over to the right-hand side, which talks about the latches. Okay, we have quite a number of latches as well. The ones that we came out about a year ago were the two-dimensional latches. These are really cool for trying to do implementations where you've got speed and direction type of, you know, maybe a volume knob. That could be a cool application. But many different types of incremental encoder applications use this two-dimensional latches. But today we're here to talk about this 1D latch, the TMAC 5115. Okay. And before I jump into that one, just wanted to do a shout out here for the DRV5013. This particular solution is, you know, one of the industry's most popular latches. You know, we sell just as many DRV5013s as we sell DRV5032s. Very, very popular latch with 30 kilohertz bandwidth, up to 38 volts. So it's a very, very, very popular solution. And then we've got the low voltage devices as well with high sensitivity, really small devices. You know, we've got 5011 that fits in a really small type of application, and so on. So, okay, without further ado, let's just go ahead and jump on the TMAC 5115, which is really what we're going to talk about today. It really is going to be I think, a very popular solution because it will operate at 60 kilohertz. So we're doubling the bandwidth. It has a very low jitter, very high speed, and it's sensitive to the Z magnetic field. Okay, all right, so let's jump to the next slide. So the TMAC 5115 is a high-speed, Hall effect latch sensor. Okay. Now we're talking. What do we mean by being fast jitter and really low propagation delay? Well, it's about in the range of 5 microseconds. Okay. If you compare that to the DRV5013, for example, we're probably 3 to 4 times better than the DRV5013, which is a really, really stellar performance. We're very, very excited about it. You know, there's a lot of benefits to getting to using a really fast, low jitter, fast propagation delay. You know, you can get a higher speed on your rotation with your motor. You can get higher efficiency with these type of devices. So it's going to be, I think, a very, very popular product as well. We have, as I mentioned earlier, it is sensitive to the Z-axis, so it's perpendicular to the surface of the package. We will have, once it's fully released, we will have several magnetic sensitivities. The first one that we released because of the fact that, you know, the 3 millitesla and the 6 millitesla, and in fact the 12 millitesla, these three here are very, very popular in the industry. So we came out with the first one. It was released a couple weeks back with a 3 millitesla sensitivity level, but we will offer the 6 and the 12 and the 1 millitesla pretty soon, you know, within a quarter for sure. So we're working on these, but the first one that came out is the 3 millitesla version. And they're available today on TI.com, by the way, if you want to get any samples. You should be able to get these specific devices. So we'll have various sensitivity levels. The main benefit to having these different sensitivity levels is you'll have a wider range of magnets and distances to the sensor available with these different sensitivity levels. All right, so it's obvious that you can vary your magnetics to accommodate these wide range of devices. What's very, very cool about this device is that we're going to have a very, very tight spread between the min and max operations, right? So if we're talking about the BOP, for example, so you can see my cursor over here on the right-hand side, the operating magnetic field, we're going tightening up this range from min to max, okay? You know, some devices in the industry can range, you know, very, very high, 5 millitesla, 10 millitesla, but we're tightening up to very, very precise min and max of 2 millitesla across the full range of devices, which is really cool. So the precision is there, and then also the really fast, the fast response time, which we're going to get to in a second. Okay, so and then also this device is a wide operating voltage, so it'll operate up to 26 volts as well. So it's very nice range of 2.7 volts all the way up to 26. There is a EBM that we have available, and it's already on the web that Isaac designed for us, and we'll talk a little bit about what more collateral we have for this device in a second. Okay, all right, let's go to the next slide. Speaking of jitter, right? So these next couple of slides, we're going to talk about the jitter and how the slew rate impacts the jitter. But if you look at strictly what jitter is essentially caused internal to the device. It's a signal chain noise, right? It's embedded within the IC. All devices have it. It's just a matter of how you control it. And it's basically right on top of the internally generated signal that was produced by the magnetic field. So if you look at this crude drawing, I do apologize, but hopefully it gets the message across. You've got jitter that rides on top of the internally generated signal, for example, right? And obviously here it's not going to go in that direction. It's going to go obviously in a vertical fashion, but hopefully you did get that message across that, jitter rides on top of the internally generated signal. And what happens is that this signal with the jitter eventually will get to a comparator, and that comparator will kind of freak out. It will not be able to determine exactly when to switch because of the jitter available. So as the device internal signal is crossing through the BOP threshold, it will, you can have a jitter as wide as this range here, right? Depending on how much your jitter is. So that's what we're trying to do, is to reduce that jitter so that we can reduce that jitter window, okay? All right, so now another thing that you need to know about is the impact of slew rate, right? So we talked about a jitter window with a slew rate in this fashion, and you'll get a jitter window that is that much, right? Whatever that would be in terms of microseconds. However, if you slow it down, what's going to end up happening is that a lot of jitter will be introduced during that BOP threshold. So that actually widens your jitter window. So we believe that when you have a unit step or a square input signal, what happens is that the jitter window is actually reduced substantially. And that's what actually a lot of competitors are putting on their data sheet. They put a jitter spec that is a 1 kilohertz square wave. I personally don't believe that's representative of what you're going to see in an actual applications. It'll be more like a sinusoidal. So I think that'll be more representative with a slew rate, not as opposed to having an infinite slew rate unit step. So what we provide in our data sheet is not only this spec, just to show you how it compares against other competitors, but we also provide another input signal to be able to, so you can really get more of what you can expect on the application level. Okay. Okay. Now, another thing to talk about with the jitter and now is the propagation delay. Okay. So propagation delay is very dependent upon the refresh period. And by refresh period, it is strictly determined by the sample frequency. We talked about earlier that the TMAC 5115 has a 60 kilohertz sampling rate, which is double than what we had previously. So this refresh period actually gets reduced in half, right? So once the threshold is crossed, you don't know exactly where it's going to cross in the sampling. It could be right at when it's going to sample, and you'll end up with a very quick refresh period. But you never know. You never know as the device is sampling. So the faster you can do that refresh period, the faster the propagation delay you're going to get. And that's truly what we are aiming for with our device, is to have a target 5 microsecond low jitter, and then a 5 microsecond propagation delay. So couple those together, you end up with a really stellar solution. And how does that actually relate to or translate to in terms of performance? Well, we think it's really a matter of system efficiency in the overall system. So jitter, the lower the jitter, the higher precision that you have, right, in the system, and then eventually what happens is that you get a higher system accuracy. But an application for that would be one we spoke about earlier with the incremental rotary encoding. You put 2 of these on a system, you can get very, very highly precise directionality and speed detection with this device. Output delay really impacts how fast you can spin a motor, right? So if you look at it conversely, the slower the propagation delay, right, which is what a lot of devices out there are, the slow propagation delay, you have a limited signal bandwidth, which means that the latency is going to get larger between the sensor and the MCU, which means that overall you'll have to wait for that signal, and you'll end up with a slower, RPM overall, right? So you can't use if you really need a high bandwidth, really fast implementation, the TMAC 5115 is the way to go. So industrial high-speed BLDC motors, for example, would be a really good use case for this. Okay, all right, so we have consumed 21 minutes. The last slide here that I would like to propose to you is looking at collateral that we have available. The product folder is available online. You can go today to and find more information about it. As I mentioned, you can get samples of these devices today. We also will provide a series of app notes, technical videos, training series, and so on. What we're working on is that we're going to have these a lot available within this quarter. It is, like I said, we just released this device, and we're going to have a slew of training material for you to look at this device. The ones that we do have available today are the brushless DC motor commutation using Hall effect sensor. It's available right now. We have a technical video that you can also look at for rotary encoding. The EVM that I mentioned earlier that Isaac developed for us is already out there. And by the way, that EVM is already in the form factor that you can put it in a standard motor, and you can very, very quickly check out its performance for that particular device. Okay, like I mentioned, we've got some really cool stuff coming out as well. The last one that I do want to mention is this here. It's called the Texas Instruments Magnetic Sensing Simulator. We call it TIMS. Okay, I'm going to give you guys a little bit of heads up of what this is all about. I'm just I would say verbally, but it is I think going to blow your socks off. I have a biased opinion, but I really think this is going to be a really cool thing to use. If you have the need for simulating the magnetic response of a device, which I think most of us do, right? When we have a design with a magnetic sensor, simulating the response of a solution with is essentially for the design. So what we're offering is this TIMS simulator, and what's cool about this is that a lot of simulations with magnetics they can be very long, from minutes to hours, and I'm not exaggerating. They can take a long time, but what we have done is that we have created this simulator, and you'll be able to get your results in a matter of seconds. Okay, really high-speed simulator and very high precision. Mind you, it's not going to be within 0.005% of error. What we're saying is that you can still get a very precise. I think we're looking at 2% of error with a really fast simulation. I think you can get highly accurate and very fast response with this TIMS simulator. So anyway, hopefully you've got the message that it's coming, and we are really excited about this as well. Besides the TMAC 5115. Okay, well, I think I have exhausted this. I really appreciate you joining us for our new product update, and that concludes our session. Thank you so much.
Thank you, Manny, and thank you for attending today's MPU webinar. The recording and PDF version of the slides will be available at ti.com/MPU. See you next week for our next topic, TPSM 33625 and TPSM 365 R6. Speed up time to market and increase your power density with these pin-to-pin buck modules. Thank you, everyone, and have a great day.